Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 26, Design of Binary Multipliers of Chapter 5, Arithmetic Network Design of the course Digital Logic Design or Digital Electronics or Digital Systems. The next slide is a disclaimer for you to read. I use 3 references, but there are many more references available. In Chapter 5, we cover design of binary adders, design of binary subtractors, design of binary magnitude comparators. Today we'll talk about design of binary multipliers. Binary combinational multipliers is logic. A binary conventional multiplier is a logic circuit that can be implemented with gates or any programmable logic devices. Also, we can use adders like full adder or adder modules. Combinational multipliers can be designed with different ways with different structure, cost, and speed. One of the easiest ways to design binary multipliers for two n-bit inputs A and B is to write the truth table that express the two n-bit product P as a switching function of A and B. Applications. Binary multipliers find applications in many fields, including microcomputers, digital signal processing, digital communication systems, and digital control. Design algorithms. Many multiplication algorithms were developed to design faster and less expensive multipliers. We will consider the following approaches: design using truth table and design parallel multipliers based on multiply, shift, and add algorithm similar to the decimal multiplication. Let's talk about the design of 2x2 multiplier using truth table. As an example of the truth table approach, we'll consider the design of 2x2 multiplier to multiply 2-bit binary numbers A and B, where A is A1, A0 and B, B1, B0. The 4-bit product P, which is P3, P2, P1, P0, was evaluated the truth table for possible valuations of the input using K-map to simplify the switching functions of P3, P2, P1, P0 will yield P0 as a function of the A's and the B's, A0 and B0, P1, A1, B1 prime, or A0 prime, A1, B0, or A0, B0 prime, B1, or A0, A1 prime, B1. P2 is A1, B0 prime, B1, or A0 prime, A1, B1. And P3 is A0, A1, B0, B1. How did we get those? Definitely from the truth table. So we have the A's, A1 and A0, the 2-digit B, B1, B0, and the output P3, P2, P1, P0. In every row, we are multiplying 0, 0 times 0, 0 will be 0, 0, 0, 0, 0. 0, 0 times 0, 1, 0, 0, 0, 0, 0. 0, 0 times 1, 0, 0, 0, 0, 0, 0. 0, 0 times 1, 1. Again, 0, 0, 0, 0. 0, 1 times 0, 0. Again, 0, 0, 0, 0. 0, 1 times 0, 1. This is 1 times 1 decimal is equal to 0, 0, 0, 1. So this is the first bit for P0 to be 1, to set to 1. 0, 1 times 1, 0. This is 0, 0, 1, 0. So P1 became 1. Because here it is 1 times 2, it is 2, 0, 0, 1, 0. 0, 1 times 1, 1. It is 1 times 3, it is 0, 0, 1, 1, which is 3. And so on and so forth until we finish the whole table, set K-maps, and we built the circuit, okay, by all NAND gate here we used. So P0, we found P0 is A0, B0. So as you can see, it is A0. This is A1 and inverted to A1 prime, A0 inverted to A0 prime line here, B1 and inverted to B1 prime, B0 inverted to B0 prime. So we have A0, B0 will give me, you take it to an AND gate or NAND followed by inverter to P0. The same thing we implement P1, P2, and P3. So we got easy implementation, fast parallel circuit, no feedback, okay, and slightly complicated because it uses many NAND gates, and we have 4-input NAND gate here, 2-input NAND gate, and 4-input NAND gate, many actually multi-input NAND gate we use, but the outcome is very good, fast multiplier. Okay, let's look at a second design example. We would like to design a 4x4 multiplier using shift add. So we have the multiplicand, which is 4-bit, the multiplier 4-bit, the B's, and the product, which will be 8-bit, P0, P1, P2, P3, P4, P5, P6, P7. And to multiply, we will take the least significant bit from P0, so B0 multiplied by everything here. So you'll get A3, B0, A2, B0, A1, B0, A0, B0. A0, B0 will represent P0, okay, because A0, P0, this is the least significant bit. Those, we call them the partial product term. They are established by a simple AND gate. So AI, BJ, the output of the AND gate will be P, IJ. So if I have A0, B0, we'll get P00. So P00 will be equal to P0. Now we would like to add A1, B0 with A0, B0. It means we are adding P10 with P01. To do the addition, we can use a half adder, or we can use a full adder with 0 carry in. Okay, if we like to use a full adder. Now this will generate a carry, definitely, right? The carry to be added with the partial product term P20, P11, and P02. So to do that, we would need definitely 2 full adders, okay, to establish this. Okay, so we go on. This will generate again a carry and will generate a sum which will be P2. The sum will be P2. When we added A1, B0 with A0, B0 with 0, give me the sum P1 and a carry out. So we're adding 4 digits here, okay? 3 digits will generate a carry, so we go and actually we need 2 full adders. And here, this will generate a carry, so we'll add A3, B0 with A2, B1, with A1, B2, with A0, B3, or we can say those in the partial product term P30, P21, P12, and P03 to generate P3, and all the carries will be carried out to the next stage. And so on and so forth till the end. And this is, we'll do it with a design of full adders. So we must use 12 full adders we would need. So we said 0, the P00 will give me P0, straightforward. However, a 0 with 2 partial product term, okay, will give me a sum which is P1 and a carry out. So the carry out with the 3 partial product term will give me the sum P2 and 2 carry out. The 2 carry out with 4 partial product term will give me the P3, and we have 3 carry out, one from each full adder. So those carry out with 3 partial product term with 1, 2, and 3. Okay, this input will be 0 because we don't have anything to add. Okay, so this will give me P4 and 3 product term with 2 full adder, and with 2 the remaining partial product term, which is the last 2. Okay, the last 2 partial product, the one before the last 2 is right here, A3B2 and A2B3, or P32 and P23, will give me P5, okay, along with 2 carries. So we need 1 full adder to add the carry with the last partial product, which is P33, will give me the sum, which is P6, okay, and the carry out, which is P7. And by doing this, we use the 12 full adder modules to implement a 4x4 multiplier using the shift add algorithm. Okay. Rather than using a 12 actually full adder modules, we can use 3 4-bit adder modules. So the 3 full adder, again, P00 will give me P0 straightforward. Now, if we look, what we are going to add, we are going to add in the next stage. So this has been processed, A0, P0, P00 will be P0, the product. Now we are going to add A1, B0, A2, B0, A3, B0 with A0, B1, A1, B1, A2, B1, and A3, B1. So since those are 3 digits, we will add a 0 here. So 0, okay, to be added with those. So the most significant bit here is 0 to be added with those in one model. Now, the outputs of this model, will be S0, which is P1, and S1, S2, S3, and S0 will be taken to the next model to be added with the next set of partial product term. If I can come here back, which is A0, B2, A1, B2, A2, B2, A3, B2 in the second module. Now, again, the second module will give me the sum as a P2 and S1, S2, S3, and the carry out to be added with the last set of partial product term, which is A3, P3, A2, B3, A1, B3, A0, B3, and the outcome will be the result, the product term, the product bit, P3, P4, P5, and P6, and the carry out will be P7. And by this, we simplified the implementation by using 3 4-bit adder modules, okay, instead of 12 full adder modules. So this is really a big saving here on the number of chips used. Standard binary multiplier module, if we would like to buy our own chips, the 74LS284, the 70LS285 are MSI, medium scale integration 4x4 combinational multipliers. The two chips together can be used to obtain an 8-bit product of 2 4-bit integers or unsigned numbers. This is the end of this lecture. I would like to thank you so much. Please subscribe by clicking on the blue circle. Hopefully to see you very soon in the next lecture. Sincerely, Dr. Hassan.